I'm surprised to see people here 5:30. So thanks for coming to this end of the afternoon session. This is not a talk about yet another database. This is not what it meant to be. This is also not a marketing talk. I don't work for DataStax or for Cassandra team. I just think this is a very useful database, and I would like to share some of my experience by getting started with this awesome database and why it could help your projects. Okay, so this is not marketing. My name is Hanneli. I'm from Brazil. I am a software developer. I've been working with programming since, I don't know, almost 10 years now. And those are the things that I like to do. I like Pokemon, so if you're playing Pokemon, please send me your friend code. Quick agenda here. Let's understand a little bit about the motivation, why Cassandra could be useful to you, what's behind the architecture, how do you write and read to the database, a little bit of structuring a data model that makes sense for Cassandra, and some combos. I'm going to leave some references for those of you who are interested to do a tutorial on getting started with Cassandra, but that's not the main goal of this presentation. I'm going to show you some intro content. It's going to be a crash course, but that's not going to be a tutorial. You can pretty much Google like Cassandra tutorial, and you're going to have those commands that you run one after the other, but that's not the goal of the presentation. We're going to see the theory behind Cassandra database and why it makes sense to adopt Cassandra in some scenarios, okay? All set? Yes? No? So this is not a tutorial. We're going to see some GIFs because I see that you're tired after a day full of interesting sessions, so that's going to help us to keep engaged with the presentation. There's going to be a point where you're going to be paying attention to this just because of the GIFs, not because of the database, I know that. So what happens, or what could it happen if you have a bunch of data inside a relational database, let's say 300 terabytes? Maybe nothing bad is going to happen, but sometimes bad stuff happen all the time. So imagine that you have some terabytes of data, and you're running a query, and it's getting slow. What could you do? Well, one thing that you could think about doing is the normalizing, creating a column called user IDs so you can avoid performing some joins by having the IDs stored in a column, right? Have you ever done something like that? Yes. The problem with the normalizing data is that, well, relational databases are not meant to be using this kind of data model, right? You're breaking rules of relational databases. So it's very easy to mess up with your data, and the DBA may be very mad at you at the end of the day. Master slave is another strategy. Do you use master slave? It's a very common strategy for MySQL, for Postgres, or many relational databases offer you this strategy. But the problem with master slave is that you have a single point of failure, right? If your master database fails, there's going to be a few seconds until the slave database assumes, correct? So that could be a big problem. Sharding. Have you ever been through sharding? Yes. I've been through sharding several times, and that's also a common strategy. But performing schema updates on sharding, on different shardings, can be a challenge. Also, imagine that you have, I don't know, you split your database, your table, in 10 different tables. Let's say you got your big users table, and you split them in 10 different slices for the sharding. So what happens if you want to run a query that's, for example, something like, you want to know the users of California. You run a single query, but for this particular query, how many queries are going to be executed? 10. You got to go through all these slices. So one query becomes 10 queries, and that can be very, very expensive. So all these strategies, they can solve some problems, but create other different ones that you never expected to have. So quick questions for you. Do you need consistency 100% of the time? for all the cases? I know it's difficult, and it's the end of the day, but please talk to me. That's not a monopolized session. Well, sometimes you might not need consistency all the time. Do you need ACID all the time? How can you ensure that you have high availability? If you're using master-slave, I can tell you that you don't have high availability all the time. Those sleep seconds that you have between the switch of a slave to a master, you're not available. So that can be a problem. So if you take a deeper look into the previous strategies, they can create you new problems. So to sum up, if you denormalize your data, you break the third normal form, and then it can cause you a lot of trouble. If you have master-slave, again, you have consistency problems, and then can cause you trouble. So the same thing for sharding. I'm not criticizing these strategies. I'm telling you that you should be aware of the problems that you can have by adopting them. There is no silver bullet. We all know that. So what would be a good scenario to have a database that can handle a bunch of data without giving me extra headache? A good scenario would be a scenario where consistency is not necessary 100% of the time. I don't have master-slave because having master-slave is going to provide me a single point of failure. I want to be able to scale my database in an easy way. I don't need to come up with more machines that I have to set up and run schema updates and things like that. I want to, I don't know, use something like EC2 and just add more machines and make sure that my database is going to be able to handle more data. I don't want to handle sharding manually because it can be really complicated to solve schema updates and so on. And that's when Cassandra comes to the rescue. So Cassandra can perform all these benefits for you, and that's the goal of the session, to make you understand why Cassandra could perform all these activities. So if you go to Cassandra website, and I know that's terrible, but you're going to see this awful 1990s page. It's like 90s page, and then that's not comfortable to, I don't know, to interact with. You're going to download a file, and there's going to be a tutorial. Like, how many of you tried a Cassandra tutorial? Was it very engaging? Sort of. Like, it's going to be like the default. So you create a schema, and then you create a users table. And then you add these columns. And then you run these commands. Like, what the hell is that? You create a schema, you run these commands, and then you, I don't know, run this query to create a table, and then you use SQL, which is very similar to SQL. What does it even mean? I mean, why would you be adopting Cassandra? So I think most of the tutorials that you find on the internet for Cassandra, they really don't tell you why the database can be helpful to your use case. They tell you about the syntax, they tell you about creating Keyspaces and tables, but they don't tell you about the features that the database has. So quick history, Cassandra history. It was open sourced by Facebook in 2008. It's mostly written in Java, although they have some code in Scala, I guess. But I think like 90% of it is written in Java. And why Java? Well, there were lots of libraries for Java by that time. They could get potential contributors to the database by open sourcing it. They were looking for a compile language that could provide them a good performance, and more than that, they had JMX to help to profile and monitor what was going on in the database. So they have a bunch of tools for profiling. They could perform a JVM tuning and get some benefits on the database. And then it was pretty convenient to manipulate data structures by that time in 2008. So how does Cassandra work? So Cassandra has a bunch of nodes. It's a distributed database. And you can see the nodes as machines. And inside every machine, there's going to be a JVM running Cassandra, a JVM with the Cassandra jar. Okay? When you get started with Cassandra, you can access all this information about the node by running a tool called node tool. And these nodes are always talking to to each other. They're always interacting. So they're like always sending messages to each other. And this is called gossip protocol. So in Cassandra, you don't have master-slave. Remember, master-slave can give you a single point of failure. And that's what Cassandra is trying to prevent. So you have all these nodes talking to each other equally. There is no master node or anything like that. They're equally distributed with equally functional, we can say that. And these nodes are going to distribute the data under a hash ring, which means that each of these nodes is going to handle part of the load. So we can think about something like that. That's easier to understand. So when you have some data being sorted here, the nodes know which is the range that every node in the cluster should be handling. So for example, you have a data that's blue, and you know that the blue data needs to end up at the blue node. And the green node knows how to send this data to the blue node. The node that receives the data is called coordinator. And this node, in this case, the green one, is going to send the data to the correct position. That's the general idea of Cassandra. I know it sounds abstract, but does it make sense having a hash ring and every participant of this ring, which is going to be a node, is going to handle parts or slice of the data? Think about a sharding, but a sharding that's always communicating between the parts. Next question, like you're talking about ranges. Where does it come from? So every time you have a table, you create a table, you provide this information here. And this information is called partition key. So in this case, it's going to be the last name. So imagine that I'm going to insert a record with my name, which is Hanneli Tavante. Tavante is my last name. So this information is going to be thrown into a hash function, and that's going to produce a number, which goes from 2 to 64, 63, I guess, something like that, which is a huge number. And that's going to be your hash. Yes, that's the correct range. You can choose different hashing functions. Cassandra provides you famous ones like murmur3 or so on. You can also add your own customized hashing functions in order to get the information that you have here at the partition key and transform that into a number inside this range here. Okay? So that's how the ranges of the hash ring are distributed. And of course, like you can have drivers in different languages that are able to calculate this token for you. One of the most adopted partitioner algorithms is the murmur3. You can also choose random or many others. So how can you guarantee availability? Because if you have a single copy, do you remember the blue data going into the cluster, and then you are assigning that blue data to the blue node? What happens if the blue node is not available? That would not be very helpful. So you need copies. And for these copies, we have the concept of replication factor, RF. We create a replication factor per key space, and key space is the structure that holds many different tables in Cassandra. And the replication factor, it's basically the number of copies that you want to have in your cluster. So how does it work? Imagine that you have a replication factor of 3. What do you so imagine that I have this data coming inside the cluster. What do you think is going to happen? How many copies I'm going to have of this data? 3, thank you. If you said 4, I'll be very sad. So this node here is going to receive this data, and it's going to make sure that this node, and this node have copies of this information. But what really happens is not one passing to the other. What happens is a replication of the range. So you can see the green range 3 times, you can see the blue range 3 times, and you can see the purple range 3 times, and so on. You replicate the ranges. So, for example, this node here knows that it's responsible for the green range, and the green range. I know that I need to replicate that 3 times. that's really what happens. You have backups of your hash rings. It's important to understand that the replication factor is going to provide you asynchronous copies. So you write once, and you're done. You don't need to wait for having extra 3 copies of your data, okay? You can ask, well, what happens if this node here that would be responsible for the green data goes down? Cassandra can also store you this data that should be written to an extra copy of the replication factor for a period of time. That's called hinted handoff. So Cassandra is also ready for this situation. So remember, replication factor is an asynchronous copy of a key space. Replication factor is per key space, per group of tables. Another thing that you might ask is about consistency. Sometimes you have queries that are a little bit more delicate, and you need to make sure that the result is going to be consistent. So how can you handle these problems? Is there a way in Cassandra to increase the consistency? Because up to now, we saw the replication factor that can ensure more copies to us. But even though we don't have the guarantee that we're going to receive the most updated slice of data. So how can we, is there a way to increase consistency in Cassandra? There is. There is another concept in Cassandra called consistency level, and that's per query. And every time you perform a query, either to read or write, you can inform the number of nodes that are going to acknowledge you back, saying that that operation succeeded or not. The same thing for reading and writing. So imagine that you are trying to read some information here. You have a replication factor of 3. And you have a consistency level of all. So you want all this replicated data to acknowledge you back 3 times. So you're going to have 3 responses, and they all need to agree. Okay? So when you have a consistency level of all, this node here is going to ask for the 3 responsible nodes, and all the 3 responsible nodes needs to perform this query and then acknowledge you back. Okay? And all these nodes here needs to agree about the information that they're going to return to you. The consistency level is per query, which means that it's not by key space like the replication factor, and that's kind of interesting because you can control the consistency of the queries that you perform. It's probably obvious that if you perform a query with consistency level of all, it's going to be much more expensive if you perform a query where you need a single response from a single node, from a single copy. Does it make sense? It's going to be much more expensive here. So again, use consistency level of all for queries that are really delicate or need very precise data. You have different levels for consistency. The default is 1. You can also use all, or the most common is quorum. We're going to talk about some problems of using consistency level of all at the end of the presentation. So it's totally fine if you have a replication factor of 3 and a consistency level of 1. Remember, the replication factor is the number of asynchronous copies that you have. And the consistency level is the number of nodes that need to acknowledge your client back when you perform a query. All right? Is it clear to everyone? Consistency level per query, replication factor per key space. So that's kind of interesting because you can have some sort of interchange between the availability and the consistency that you want to provide in certain situations. Of course, if you require too much consistency, those queries are going to be expensive for the cluster, and they're going to require more machine time. So you can measure according to your needs. So how do you read and write data in Cassandra? So to simplify the process, imagine that you have some data here being written. And then once this data reaches the node, 2 things are going to happen pretty much at the same time. A commit log file is going to be written on the disk. It's a single flush on the disk. It's not an order structure on the disk. It's just a flush. And then a structure is going to be created in RAM. This structure is called main table. That's going to represent the information that you're actually inserting on the cluster. And then once it's done, then you're going to acknowledge back, you're going to acknowledge back to the client, okay? You only need these 2 quick actions in order to have a successful writing in Cassandra. Once that is done, after a while, asynchronously, this structure that is in memory is going to be flushed in the disk in another structure, and this one is a sorted structure, indexed structure that's called SS table, all right? But this is asynchronous. You don't need to come up with an SS table in order to acknowledge back to the client, right? And all the data comes with timestamps, so everything in Cassandra is immutable, which means you can't really perform a delete. You're not really removing the thing there, you're just marking that as, I don't want this piece of data anymore. You can't really perform updates. You're gonna write new records and so on. So that provides you very fast write, okay? So every time you write in Cassandra, those 2 actions here, creating a structure in memory plus flushing a single file in the disk, are very quick actions. Does it make sense? Yes. Please talk to me. I know it's the end of the day. Come on, you can make it. So a problem here is that for every write, at some point, you're going to end up with this annoying structures called SS tables. Isn't it really annoying? Do you think it's healthy for your disk to have this kind of structure? Of course not. So from time to time, Cassandra needs to perform some sort of compaction to grab all these SS tables together and combine them and provide better indexes to the information that you're actually writing. So again, the name of this is kind of obvious. It's called compaction. And they have different algorithms for compacting your data, all right? Again, this is necessary because you're going to end up with a bunch of SS tables on your disk, and that's really bad for performance. So it's better to have like a little bit larger files that you can actually check them instead of like really small chunks of data. So how do we read data? So imagine that you have a query here, and this client is asking for a piece of information. It's much simpler. So Cassandra just goes to the SS table, finds the data that it wants, and acknowledges back to the client. This SS table here, again, it has a bunch of levels of indexing, and it can return your data in a very fast way. For consistency level of quorum and all, what really happens is that Cassandra is going to read the data from all the nodes, if the consistency level is all, and then it's going to agree on the most recent one in case you get a different result. So let's say this node got returned to you like 1, this node returned to you 2, and this one returned to you like 4. So Cassandra is going to try to find the most recent information. Remember, all the information that you write comes with a timestamp, and it's going to return you the most updated one. And not only that, after acknowledging back to the client, Cassandra is also going to update the outdated nodes. So that's quite convenient. So every time you perform a query, and Cassandra realizes you have outdated information, it's also going to update the outdated nodes for you. So how can we structure our data model? So remember that I mentioned that Cassandra was created at Facebook? And Facebook, you have something like that. You're a user with a bunch of posts, and every post can have a comments and a like. So can you picture this scenario? It's a nested structured scenario. So Cassandra came up to solve this kind of problem. In a similar way, we could think about a music application where I have playlists and tracks and a bunch of artists. And see, this information could be repeated in different, for example, artists could be repeated for different tracks. The same artist could be present in different tracks, but in different playlists, right? So turns out that it can be messy to try to solve this kind of problem inside relational database because you would need self-relationships and so on. So Cassandra comes to solve, and in a good way, this kind of scenario here. So how do we create our data model? We are going to have a bunch of replicated data. Again, the same way an artist can be in different tracks of different playlists, we are going to write this data, replicating it across different tables. So to give you an idea, for a music app, we would have tables like track by ID, track by user, track by artist, track by style, and things like that. Right? So we are going to have replicate the track information across several tables. And that's going to provide us a good speed to fetch data. So one thing here is that Cassandra doesn't have group by, so you got to rely on clustering columns. And best combos. Cassandra works pretty well with Spark. If you're working with event sourcing or event tracking, for example, it's a good combo because it can provide you fast read and fast write. Again, Cassandra, Spark, and Kafka, if you have some sort of real-time streaming. Cassandra and Solar can provide you an interesting way to use text search with a database. And Cassandra is very flexible, and it's open source, so you can pretty much create a connector or a new framework that can make Cassandra interact with it. And then how can you get started with Cassandra if you're interested? I totally recommend this project called CCM. The thing with Cassandra is that you need more than one machine, at least. So with CCM, you can kind of mock your own local environment to make it look like a cluster with different fake IP addresses. And you can pretty much work simulating a local cluster on your machine. I also recommend DataStax Academy. They have very interesting courses, and they're free. And here, also some reference for you. In my last minutes, I want to talk about Cassandra complaints. One of the top Cassandra complaints is about the garbage collector. But it's not only, it's not really Cassandra. It's more about the GC on Java. People found different bugs on Cassandra because of that. It's not an issue, but some people, sometimes they complain about the GC. Another thing, from time to time, you need to update your information. So if you don't have queries that run on the consistency level of all, how are you going to perform an update for the outdated nodes? So from time to time, you need to run an operation called read repair. And that's going to update your outdated data. The last thing here is about the consistency level. If you have the consistency level of all, you require that all the data that have a certain information to acknowledge you back. But what happens if one of your nodes is down? Your query is going to fail. So be careful with consistency level of all. That's why I told you, focus on using consistency level of quorum, which is going to provide you a very reasonable consistency. Sometimes modeling can be another struggle, because if you're coming from relational databases, you're not used to create a bunch of tables replicating data. And that also means that you need a bunch of space on disk. So be ready for getting SSDs on your infrastructure as a service. So I'm sorry this session was really quick, 30 minutes only. But if you have any questions, I'll be around, and I'll be help you to get started with Cassandra. So thank you very much.